In this video, we are going to discuss about TTT diagram, which is in the second unit of Material Science, PH 8251. Course outcome. Upon completion of this course, the students will be able to explain the TTT diagram. The TTT diagram is nothing but temperature time transformation diagram. It is also called isothermal transformation diagram. It is a plot of temperature versus the logarithm of time for a steel alloy of definite composition. It is used to find when transformation begins and end for an isothermal heat treatment of a previously austenized alloy. When steel is austenized and then held at a constant temperature below the austenite region, it will transform to some transformation product like pearlite or bainite. There is an incubation time for nucleation followed by nucleation and growth. Finally, the reaction will be completed and then the transformation will be finished. The course of this transformation can be understood by plotting the amount of austenite transformed against the corresponding elapsed time at constant temperature. For a given steel, the information given by a series of such curves, each curve determined at a different temperature, can be summarized by a single diagram called a time temperature transformation curve. This curve is shown in the following figure. Here we see what is TTT diagram. In this picture, the time is plotted along the x-axis and the temperature is plotted along the y-axis. At first, the eutectoid alloy is heated up to a particular temperature, that means above 700 degrees centigrade. The temperature is called as the eutectoid temperature. Above this temperature, the material is in the austenite phase. In general, there are two important phases for the eutectoid alloy. The first one is the austenite phase, which is usually occurs at high temperature, and another one phase is the martensite phase, which is usually occurs at low temperature. So in this TTT diagram, how the austenite is slowly transformed into another phase, that is called as pearlite. Then the temperature is reduced so that the pearlite is slowly transformed into bainite, and further reducing the temperature at about 100 degrees centigrade, the bainite is slowly transformed into martensite. So that is clearly represented by this TTT diagram. Here we see at about 750 degrees centigrade, the material is in the austenite phase. When the temperature is decreased from this 750 degrees centigrade to about 500 degrees centigrade, the austenite is slowly transformed into pearlite. Further decreasing the temperature and the material is held for some time. That is very important. Now at this temperature, when the material is held for some time, the pearlite is slowly changed into bainite. That means at about 300 degrees centigrade, the pearlite is slowly transformed into bainite. Further decreasing the temperature, and the temperature reached at about 100 degrees centigrade, and the metal is held for some time at this constant temperature, the bainite is slowly transformed into martensite, which is the lower temperature phase of the eutectoid alloy. So this transformation is clearly indicated by two curves. The first curve is called as the transformation begins curve, and the second curve is called as the transformation ends curve. So in between these two curves, the transformation takes place. This curve is in the shape of English letter S. So this diagram can be thought of as a map which plots the transformations of austenite as a function of constant temperature and time. This allows estimates to be made regarding how the steel will respond to any mode of cooling from austenite. Here we see how the austenite is changed into martensite. When the austenite is slowly cooled, it is slowly transformed into pearlite. Then it is moderately cooled, it is slowly changed into bainite, and for the rapid cooling process, it is slowly transformed into martensite. So, due to the cooling processes, the internal structure of the steel is slowly changed. That means the atoms inside the material is slowly transformed from one position to another position, so that the structures of the austenite is slowly changed into pearlite, then bainite, and finally it reached the martensite phase. All those structures are clearly given in the picture. So from the diagram, when austenite is cooled slowly to a temperature below lower critical temperature, the structure that is formed is pearlite. As the cooling rate increases, the pearlite transformation temperature gets lower. The microstructure of the material is significantly altered as the cooling rate increases. By heating and cooling a series of samples, the history of the austenite transformation may be recorded. Now let us see the applications of TTT diagram. The TTT diagram can be used to specify the nature of the final microstructure and approximate percentages of the phases that are existing at room temperature according to certain heat treatment path. So that by heating the material and held the material for some time and the material is cooled, so that the different types of materials will be manufactured. One of those applications is given in the figure. So in this video, we have clearly discussed about the phase transformation of the eutectoid alloy. That is, how the eutectoid alloy is transferred from austenite phase to martensite. But in between these two phase changes, how the metal is changed from austenite to pearlite, then pearlite to bainite, and finally bainite to martensite. Thank you.